Hey friends, there's an age-old discussion among theologians as to when we look around, what all did God make and what did humans make? So for example, if we look at the planet Mars, it's pretty easy to say, yeah, God made that. I had nothing to do with it. And I look at myself and God made me. I'm not here because I decided to be. Well then, how about I'm an introvert? So did God make me an introvert or am I responsible for that? Or we look at the painting, the Mona Lisa. Did God paint the Mona Lisa or did Leonardo da Vinci? And how about your last History and Foundations reading quiz? Did God do that work or did you? And if you say God did, well, why did God get a B instead of an A? I don't know. That spills over into mathematics, and that topic is going to come up in today's lesson. So for now, I'll just leave you with an opinion from somebody from the 1800s that said God made the integers, 1, 2, 3, 4, and so on, but everything else is the work of man. So things like matrices and functions and real numbers and so on. Interesting question. Today's lesson is the second part of chapter 13, dealing with the early 19th century. So this is like 1820s to 1860s. And the topics we want to talk about is what's meant by 19th century. Eves calls it liberation. I might call it abstraction. But anyway, what do we mean by that term? And to get at that, we need to look at some examples. And Eves talks about how geometry was liberated and how algebra was liberated. So if we look at some of the details here, I think you understand what liberation means. And then briefly talk about mathematical societies. So first of all, geometry. Let's go back to Euclid. Euclid started with 5 postulates, things that he said he was going to assume rather than prove. And his 5th postulate, he didn't state exactly like this, but let's take an easier way of saying the idea that given any line L and any point P not on L, there's exactly one line through P that's parallel to L. So in this picture, that would be marked M, and these dotted lines would not be parallel. We talked about this in transitions a great deal, so I won't spend much time on the mathematics. Here we want to talk about the history and philosophy behind it. So Euclid had 5 postulates, and the 5th is by far the least intuitive. There's some speculation, in fact, that Euclid was uncomfortable with his 5th postulate because he seemed to write as many theorems in the elements as he could before he finally broke down and used the 5th postulate. Because it seems so less natural than the other 4 postulates, between Euclid's time and 1800 AD, many mathematicians tried to prove Euclid's 5th postulate. In other words, try to show that it wasn't a postulate at all, that it could be a theorem. So in his transitions, we talked about Zachary quadrilaterals. His quadrilateral has 2 right angles at the base and 2 congruent sides here, and then talk about what happens with angle A and angle D. But even though there were many attempted proofs at Euclid's 5th postulate, all of them were eventually found to have flaws, so they weren't proofs at all. And by the early 1800s, it was starting to come to people's mind that maybe we can just say that given any line and any point not on the line, there is more than one line through P parallel to L. This was done independently by Carl Gauss, whom we've already met, and then people named Lobachevsky and Bolyai, again around 1825 independently. It's not that this question has a right answer. It turns out that it's just how you want geometry to behave. So when we make this choice of postulate instead of Euclid's choice, Then we get what's called hyperbolic geometry. It's neither better nor worse than Euclidean geometry. It's neither more real or less real. It's just different. It's a choice of what kind of geometry we want to study. And this gets at what Eves calls the liberation of geometry. Related to the question, is math a discovery or an invention? So in the late 1700s, the philosopher Immanuel Kant got into mathematics and said that, hey, Euclidean geometry is just inherently true. It's the real geometry. It's imposed on our human minds, maybe by God himself. And so no other postulates really can be logically consistent. It's wasting our time to think about alternatives to Euclid's parallel postulate, even if we can't prove it. So that would go along the line that mathematics is really linked to the physical universe. And just like astronomers discover planets and stars, mathematicians discover theorems and definitions and so on that have already been um, created, perhaps by God. But the discovery of hyperbolic geometry means that Euclidean geometry is just one of several possible choices of geometry, depending on which postulates we choose. And that would tend to lie in the camp that math is invented by humans who can just choose whatever rules they want as long as they are logically consistent. Let's look at algebra. So arithmetic is a subset of algebra. In arithmetic, we add and multiply numbers. In algebra, we add and multiply and do other things to variables. In arithmetic, we know that addition is commutative, multiplication is commutative, addition is associative, multiplication is associative, and multiplication distributes over addition. And there are other things as well. So these are axioms. We believe them because every time we go out and start moving pebbles around in different ways, these rules always happen. 3 stones plus 5 more pebbles make the same as 5 pebbles plus 3 more. And one viewpoint then is that since algebra really is just arithmetic in fancy clothes, in other words, it's just representing numbers using unknowns for a moment, then these axioms of arithmetic are really true for algebra as well. And they're inherently true. It doesn't make any sense to think about an algebra where these axioms do not hold. So we want to focus in particular on multiplication is commutative. Here's an Irish gentleman from the early 1800s who was trying to extend results from physics from 2 dimensions to higher dimensions. So in physics, mechanics, there's something called the Hamiltonian now. And Hamilton looked at complex numbers. At the time that he started working, people thought of complex numbers as we teach them in high school. Here's a number a plus b times I, and here's a number c plus d times I. If I want to multiply these 2 complex numbers, then I should FOIL them out and remember that when I get a term like b d I squared from the product of the last 2 terms here, that I squared is -1. And so if I FOIL this out, I get another complex number like this. And Hamilton said, well, really, the I and the plus part are not essential. They're kind of just placeholders. Because if I just say that an ordered pair AB times an ordered pair CD behaves like this, then I have the same thing as the multiplication of complex numbers. Furthermore, this is a generalization of multiplication of real numbers. So a real number is just a complex number where the imaginary part is 0. So if I take the complex number a comma 0, or a plus 0 times I, times the complex number c comma 0, and apply this definition of multiplication of coordinate pairs, then I get that these two complex numbers multiply to this one. In other words, A times C is A times C, and 0 and so on obeys the usual rules for multiplication. So this multiplication of complex numbers has generalized multiplication of real numbers. And Hamilton said, well, can I take this idea to higher dimensions? So can I take a four tuple, a grouping of four unknowns or components, and somehow make a multiplication with another grouping of four components? He was able to do this, and the expression is in the text. It's messy and not really of the main point of interest. But some of the points of interest are that when we take a two-component vector with zeros in the last two slots and another two-component with zeros, and I multiply those according to Hamilton's rule, that I get the same expressions as I got from complex numbers. So what Hamilton called the quaternions with four component vectors generalizes the complex numbers. Quaternion multiplication generalizes complex number multiplication. Well, complex numbers are useful, so maybe quaternions would be as well. And so Hamilton thought he was onto something, but there was a problem that bothered him. By his definition of quaternion multiplication, multiplication was not commutative. And everybody knew that multiplication had to be commutative, and so Hamilton says, what am I doing wrong? So the story goes that he's out walking with his wife on some romantic evening, and it occurs to him that multiplication doesn't have to be commutative. That's the part to throw away with. Keep my definition of quaternion multiplication and don't worry about the fact that it's not commutative. And so I believe this is factual, that he was walking by a bridge at the moment and pulled out his pocket knife and carved his discovery or a part of it on the bridge. He was just so excited. The bridge was wooden and it's long gone, but at the site there is now a plaque that says something like Hamiltonian recorded his great discovery here in 1843. You've taken linear algebra, so you know another example. Here's a gentleman, Arthur Cayley, from roughly the same time period, who was actually one of the first people to come up with the idea of matrices and how they work. It's one of the most surprising things to me in the history of mathematics is how late the idea of a matrix came up. People were working with systems of linear equations back before the time of Christ, and so their matrices are so useful for those. Why did it take people so long to come up with? Cayley worked with matrices, and he defined matrix multiplication as you learned it in linear algebra. And as you probably also learned in linear algebra, multiplication of matrices is not commutative either. And so this added to the confirmation that came with Hamilton's discovery of quaternions, that now most mathematicians think of it this way, that axioms of arithmetic are just one of several possible choices. When I say that arithmetic has to act this way, well, I just based some things on how my everyday life seems to work and say that's how it has to be. But a mathematician, a pure mathematician at least, would say, no, that's not how it has to be. You can make it be that way if you want. In fact, axioms of algebra can be chosen in any logically consistent way I like. And so now, if you have taken abstract algebra, the rest of you will. And in abstract algebra, we multiply lots of things. We multiply functions, we multiply geometric rotations and translations, we multiply matrices and vectors and so on. And for each type of object, the definition of multiplication is somewhat different, and yet there are some standard rules that multiplication obeys. In abstract algebra, we go ahead and study things called groups, rings, fields, etc., etc. At this point, mathematicians, or Eves at least, would say that algebra has been liberated. No longer do I have to think about numbers and what's true about numbers. Algebra is its own discipline. It's actually now one of the largest branches of mathematics. And finally, a brief discussion of mathematical societies. So these are groups of mathematicians, usually professional mathematicians, who do things like publish journals, organize meetings, maybe raise funds for mathematical causes, lobby governments to vote for policies that are good for learning mathematics, recommend best practices in teaching, etc. So the concept goes back a little farther than that, but the ones that are most familiar to us as coming from a European heritage are the Royal Society in England and the French Academy in France from the mid 1600s. We live in the United States, and so there are many mathematical societies in the US, but three important ones that deal with education are the American Mathematical Society, which focuses on graduate and research level mathematics, the Mathematical Association of America, which focuses on undergraduate college level mathematics, and the National Council of Teacher of Mathematics, focusing on secondary school. So these are all from around the time of 1900. Some of you may have gone to a meeting of the AMS and MAA, the joint meetings, for example, in January. As a professional, if you work in mathematics, you might consider joining one of these professional societies, partly for benefit for yourself to learn some things and keep learning things, and partly out of a sense of professional duty that it's your job to help advance the cause of mathematics by helping a society do these things. And we will stop there.